Hello, I welcome you all to this another interesting screencast, and in this particular problem we are only going to be dealing with case 2. Remember we solved case 1 which is 11-13. If you've not watched it, you can just get back to the previous video. 11-13 was solved, and this is where we collected all this work. We collected all this work from the previous video, and we just changed on the value of k. Okay, so let's read the second problem. Each member of the pin, we are reading this problem here. Okay, each member of the pin connected mechanism each member of the pin connected mechanism has a mass of 8 kg. If the spring is unstretched when theta is equal to 0 degrees, determine the required stiffness k so that the mechanism is in equilibrium when theta is equal to 30 degrees. So here they've already given us theta to be equal to 30 degrees. Okay, so theta is equal to 30 degrees at equilibrium. All right, so theta here is equal to 30 degrees at equilibrium, and they're asking us to find k. Okay, so let me just briefly talk about this. Of course, even in this second problem, we want to use the virtual work method. So what is the virtual work method? This is an alternative method to the equilibrium of equations of equilibrium method, or equilibrium method for a particle, equilibrium method for rigid body, equilibrium method for interconnected rigid bodies. And if it is an alternative, it means we can solve this particular problem by using the equilibrium method. All right. So what is virtual work? Virtual work itself is states that the total work in a system like this, which is interconnected system of interconnected rigid body, the total virtual work is equal to 0. And this virtual work can be contributed due to product of translational forces and translational virtual displacement del R. It can also be contributed due to a product of a couple moment and rotational virtual displacement. And when we sum up all these virtual works, is equal to 0. Given a force and given a translation of virtual displacement del R, for virtual work to exist, the two must be collinear. And if they are in the same direction, then we have positive virtual work, otherwise we have negative. The same applies to a couple moment M and virtual rotational displacement del theta. For virtual work to exist, the two must be parallel or collinear. And if they're in the same direction, then we have a positive virtual work, otherwise we have negative. In brief, this is the method that we want to use and what it is. So like I said, we've already written equations in advance because we did the first problem, so we are on the second problem. Okay, 11-14. All right. So of course, the first step is always drawing the free body diagram. So the first step, we drew the free body diagram. Okay, so there's a free body diagram for the forces, and the free body diagram after the structure is after we apply a virtual displacement. So we applied the virtual displacement at C. Okay, there we applied the virtual displacement there, and then after that we had to draw the configuration of the displaced or deflected system. And after we did that, then we had to now we had to choose A as our fixed reference. So we chose A as our fixed reference, as shown here like this. All right, and once we did that, then we had to now define all the positions. We are interested in the positions that are going to cause the virtual work, and those are positions that has both translational force and translational displacement, and they are collinear, or they have rotational displacement and a couple moment. Okay, and the two are collinear. All right, so those were the points that we're interested in. So for the translation of virtual points, okay, so we had YB, and we are referring them from our reference point, which is A. So we had YB, we had YF, we had YG, okay, and we had also YE. So we had to write them down. So this was YE, okay, from A, and then we also write down the virtual displacement del YE. So we had YB there and this virtual displacement in that manner. We had YF there and this virtual displacement in that manner, and we had YG and its virtual displacement, and of course we had del theta A, which is just equal to del theta. All right. Also, we wrote down what the friction, what the spring force is. We know spring force according to Hooke's law is equal to K times S, K being the spring constant and S being the stretch. All right. And then we know that S is equal to L final minus L original, and we've been told that L original is 0. You can think of it of just 0, L plus 0, but the L will still cancel out its original length. So it's just 0 at theta equal to 0 degrees, and L final is just equal to 0.3 sine theta, which is just equal to YB. Okay. And then therefore the Fs, which is the spring force, is just going to be equal to that, and finally equal to this 0.3 K sine theta, because we want to find K. All right. So then we had to plug in all these particular virtual displacement in our virtual work equation, del U equal to 0. Okay. So we had this equation here written down. We plugged in all the values, and like I said, the points that are going to have virtual work are point A, point E, point B, point F, and point G. So M is equal to 0, right? M is equal to 0, all right? M is equal to 0. This M here is equal to 0, right? In this particular case, therefore this part here will be 0. Okay, this part will be 0. This part goes to 0. All right, so we just remain with the other parts there, and these are the parts that we want to just concentrate on right now. So let's write them down. These are the parts, right? So W will just be equal to, we calculated it, it's just 78.48, then times del ye is just 0.15 cos theta del theta. Okay, and then we have Fs minus Fs is 0.3 K sine theta, and then this by del YB, which is just 0.3 cos theta del theta, then plus W, which is just 78.48 del YF, which is just a 0.3 cos theta del theta. All right, and then we have another value of W, which is 78.48, and then we have del YG. Del YG is just 0.15 cos theta del theta. Everything equal to 0. So if we are to summarize this, we have 78.48 by 0.15 plus 78.48 by 0.3 plus 78.48 by 0.15. Of course, this gives us, so we factor out del theta like so, then we have a 47.088 cos theta. Okay, and then we have the other part there, which is a 0.3 by 0.3. So this just gives us as a minus 0.09 sine theta cos theta equal to 0. So we know this part del theta will not be equal to 0. Therefore, the only part that will be equal to 0 will be this part only. So let's write down that part. So we have a 47.0 sorry, there is a K somewhere. This one is not well written. 0.99 K. Let me write down the K. All right. So this is 0.09 K sine theta cos theta. All right, it's like that. All right, so now then we have that equation inside like so. Cos theta minus 0.09 K sine theta cos theta equal to 0. But we've been given theta is equal to 30 degrees. This is theta at equilibrium. Okay, so we want to find the value of K. So if we are to plug in theta in there, then our K just becomes equal to, 47.088 cos 30 divided by what's the value there? We have a 0.09 sine 30 degrees. Okay, let me write this properly. Sine 30 degrees cos 30 degrees. All right, therefore K is just going to be equal to, that's 47.088 cos 30 divided by 0.009, that's 0.09 sine 30 cos 30. All right, so this gives us 46.4 newtons per meters. All right, where are we? Let's work it again. 47.088 cos 30. Okay, 09 sine 30 cos 30. All right, 1046.4. Great. So this is the value of K that will allow this particular system to be in equilibrium at 30 degrees. All right. I know this was a bit shorter because we did most of the work in the previous video, so we just had to import what we had done on the previous case. So I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.